We have introduced the space of Hajlasz-Sobolev functions. Recall that the function belongs to M1P if U is in LP, and there is another LP function which behaves like the derivative of the function U in this sense and in no other sense. Recall that this space is defined under basically no restrictions on the measure and the distance. Even the measure is not assumed to be doubling, which is usually the minimum you assume for good results. So per definition, we don't need that. And in this generality, we prove that the space is a Banach space, that the PP Poincare inequality holds on this space, provided that the measure is finite, measure of the space, and that Lipschitz functions are dense in this space, which are properties that are already very different from the class of Newtonian Sobolev functions that we will define later. So if you are in an open subset of a Euclidean space, we have now two competing notions of Sobolev functions. The one that comes from the classical theory using weak derivatives, integration by parts. And now we have M1P, where omega on its own is thought of as a metric space. The measure on it is the restriction of the Lebesgue measure, and distance is the inherited distance from the Euclidean one. So when are these two spaces equal? That will be the question that we will talk about today. So first of all, we can easily show that these are not in general equal. And there are multiple ways of doing this, and one way is to observe that if, excuse me for that noise, so if E is a subset of X with zero measure, then the space M1P of X minus E, so X minus E on its own is again a metric measure space with inherited distance and measure. This space coincides with M1P of X in the sense that to every function we can uniquely associate a function in the other space with equal norms. So it's as Banach spaces, they are equivalent. And why is this true is simply because of the definition. If you start in some function here with an upper gradient, then the restriction to X minus E and the restriction to X minus E of G together will form a pair where G will be the Hajlasz gradient of U restricted to X minus E. And going backward, we can, if you start with a function pair defined on X minus E a priori, then you can just set U to be 0 on E and to be equal to the values on X minus E. And then do the same with G, and then you see that the inequality in the definition holds almost everywhere because, well, the set E doesn't come into play anyway, so you toss that into this part N, so N union E will be the exceptional set. So removing a measure zero set does not change the class of Hajlasz-Sobolev functions, and this is very different from Sobolev functions in the classical sense. So the corollary of this will be that for some open subsets of Rn, W1P of Rn will not be equal to M1P, omega of omega. We can, in the parentheses, emphasize that for any value of P. So proof of corollary just take, for example, Rn minus just one single line, infinite line. And I'm going to intentionally draw it like this. So suppose omega is everything except this line on R2, for example. Now, if you take the function u to be constant 1 on this side and constant 0 on that side, then you can easily check that the integration by parts against compactly supported smooth function in omega, that means they will vanish near this line. If you test, you will see that 0 is a weak gradient of u. Of course, you can also multiply by a cutoff function to have these become 0 also again here, so that you technically have an LP function. From this, you see that u belongs to W1P of omega. It has a weak derivative that is integrable, this 0. Integrability of u itself, again, is not often a significant thing. Even there is a class of functions where you only care about integrability of the derivative. So anyway, this belongs to W1P, but u has no extension, so to a function on W1P of all of Rn. That follows from the ACL characterization that on almost every horizontal line that you cross, the function has to be absolutely continuous, and we see that in none of these it's actually absolutely continuous, because it's 0 here and it's 1 here. If you change the representative of the function, again that property fades. So remember these properties of Sobolev functions that we dedicated a full video to, and one of the properties was that the Sobolev functions are actually more restricted than just being defined up to a set of measure 0. So that shows that this space cannot be equal to that space. A related example maybe first we should talk about positive examples. W1P of all of Rn is indeed equal to M1P of all of Rn, and that this is how actually one motivates definition of M1P. First, you basically prove that if you define a class by M1P, you recover a coordinate-free characterization of Sobolev functions on Rn, and that motivates the definition in general settings. So this is true, and also W1P of any ball in the Euclidean space is equal to M1P of any ball in the Euclidean space. So R between 0 and, given the first case, also infinity. So these are the results in the affirmative when these spaces are equal. We saw an example where they are not equal. Another example will be the slit disk. So this is a go-to example in many scenarios. We will come back to this again and again because it's an easy example to test some questions. So you have the ball minus one radius, not the full diameter, just one radius. So one simple segment is removed from this ball, and let's call it B prime. So Heinonen has some argument, and later he refers to that to argue that M1P is the same as M1P of B primes. We saw that also in the previous lemma, that we just remove a set of measure 0 and these are equal. But I have also another suggestion for the proof, and that was the density of Lipschitz functions. We saw that Lipschitz functions are dense. And notice that the Lipschitz function on B prime is just the Lipschitz function on B itself because, well, Lipschitz functions uniquely extend to the closure of a space. The values on this and this side are close because of global, remember Lipschitz is a global condition. So these are similar values on two sides. So you can uniquely define a function, if a Lipschitz function that is defined on B prime uniquely extends to a function on whole of B. From that, maybe I'm wrong, but I believe there is an easy argument why these two spaces are equal. So the Lipschitz classes are the same for B and B prime, and their closure in that norm, which is the same for these classes, then their closure becomes equivalent Banach spaces. But anyway, so let's take this now as truth that this is correct, but W1P of B is not equal to W1P of B prime. There are many more functions in this one. And the reasoning is, again, you can have a smooth function that is one value here, starts with constant 0 about in this neighborhood, and then it's equal to 1 to this side, and it smoothly actually can have a distinct infinity function that goes from here to here, but it is not in the Sobolev function of here. So it belongs to that function, but it does not belong to here because, again, of the absolute continuity on almost every line. If you drop parallel lines that go through this, then this function that I described with value being 0 here and 1 on this side will not be absolutely continuous on either of them. And that's a large class of lines to fail absolute continuity on. So in this case, you will see that the consequence of these two observations will be that M1P of B prime is inside but not equal to W1P of B prime. Remember that this is equal to this from above. So this is equal to that, which is strictly included in this one. Okay. Now I want to relate to you two results regarding this question of when, for what type of domains does this hold. So we first introduce what is called a measure density condition. Again, omega is a subset of our n that is open. So the measure density condition is defined very simply. So you take a ball, mostly we're interested in the boundary points, and a ball of radius r, and you measure how much of it picks up from inside the domain. So you intersect omega with ball centered at x radius r. You look at its measure. So this common notation for the measure. So I don't know if this is r2 or rn. So I just put this to avoid mention of that. So we say that this is a certain percentage, at least it picks up C% of the measure of the full ball itself. Of course, this can fail if for simple domains like a ball, if the radius is allowed to be extremely large. So this is for all r smaller than a threshold, and often just 1 is enough. So if a domain satisfies this. We say omega satisfies the density, the measured density condition if this holds. So let's call it star. So this avoids some very bad domains like those with a very sharp cusp, which I failed to draw. Okay, now it's being too good. So if in this domain, okay, this is annoying. Okay, in such a domain, when you pick your x here, and if this is a faster than polynomial, I think polynomial itself is good enough, or you can imagine this is an exponentially shrinking domain, then you see that if you take x here, then this condition will fail because your balls around here will pick up almost 0%. This c will be worse and worse as r becomes smaller. So this is an example where this condition fails. Okay, so what does this have to do with equality of the W of the W1P and M1P spaces? Okay, a second definition we need is that we say omega is a W1P extension domain if there exists a bounded linear extension from W1P of omega into W1P of Rn. We saw in the slit disk example, also in this Rn minus 1 line, that those were not extension domains. You started with some function in the domain, and you couldn't define it on the closure of it or extend it to all of Rn because of failure of absolute continuity. So if a domain is nice enough, we will have this existence of such an operator. And boundedness here is in just terms of that when you start with this function, so if this is called e, that e of u, which is a function in Rn, when restricted to omega, is this same function you started with here, in the sense of, you can say almost everywhere, for example. So it really extends, so that's the only meaning of extension that could be there. And boundedness is in the norms of W1P. Okay, so this one is from a 2008 paper by Hajlasz, Koskela, and Tominen, that for p between 1 and infinity, this star condition and equality of M1P omega with W1P of omega characterizes W1P extension domains. And the second part to this is that for p also including 1 this time, if omega is a W1P extension domain, then this star holds. Sorry, in this star we forgot to say that an X belongs to omega closure. So I also said that this is interesting for boundary points, because if you're in the middle and for a small radius, well, the whole ball is inside the domain. Okay, so let's unpack this result. First of all, if you are an extension domain, then you do have the density condition. So this cusps will not be, sharp cusps will not be extension domains. So there will always be Sobolev functions here that have no, that are not restrictions of a Sobolev function defined on all of the space. Okay, so the first part is a bit tricky. It's not saying that you are an extension domain if and only if M1P is equal to that. It's if you have a star, then these become equivalent. So in the presence of the density condition star, being an extension domain is equivalent to the equality of M1P omega and W1P omega. So basically the question reduces to identifying W1P extension domains in the case that we do have the measured density condition. But the bad news is that actually identifying the W1P extension domains itself is a very difficult question, and I think it is far less than perfectly known. So there are definitely many questions still remaining there. I think in the case of plane, just R2, we have some very good results, but in the very generality, maybe still many open questions remain. So something for you to research about. The second result that I want to talk about is a bit more recent, and this is by I think, if I'm not wrong, it's 2021 by Koskela, Eriksson Beek, Jan Molly, and Zhu. So what they prove is they look at domains where you have, so what they do is, suppose you are in R2, but this can be also done in other dimensions as well. So you have x, y, and then you have a function phi here, graph of the function, which is not as smooth as I drew. Now you want to rotate this, the thing you did in calculus 2 to compute the volume or surface area of these stuff, the washer method or some things like that they called them. So you just rotate it and you get a domain. And to avoid the cusp here, so if you have like this and you rotate, there will be more cusp-like behavior here. They also add this constant extension at the end, so that will provide the full cylinder part to it. Okay, so they produce then something like this. Okay, and then they prove that under quite very general conditions, basically you just need nothing other than making the smallest assumptions on this phi, so that this is actually a domain, an open set. So, and I think the result is basically if phi. So my laptop ran out of battery in the middle of my recording and died, so I can't quote the exact result, but basically it is that if phi is a monotone left continuous, again this is just to make sure it is actually a well-defined domain. Then this domain that we produce by this is okay, then this domain satisfies M1P omega equal to W1P of omega. So this is an interesting example because it's not covered by the result of Heinen, Koskela, Tuominen, because in this case, the space, as I mentioned, because of this cusp at the end, fails the measure density condition. So therefore, we don't have the equivalence that we wanted. Actually, this space then is not an extension domain because of the second part. So it's not an extension domain, but nevertheless, we have m1p of omega equal to m1p, w1p of omega for this. There must be some other results regarding these that I am unaware of, but probably these are places to begin with if you're interested in such questions. So finally, we are at a place where I can relate to you my limited list of maybe interesting open questions in this area, and you could research about them and begin investigating and trying to find some results of your own. Okay, so that gives us many examples of Sobolev-Hajlasz class, incidentally, because, well, there are many domains that satisfy the density condition and are extension domains. So then M1P becomes just W1P. Maybe I should mention that bounded Lipschitz domains are W1P extension domains. For all P. This is, for example, proved in Evans and Gary P, and also in many other books on classical Sobolev theory. So if you have a Lipschitz function, for example, the graph under it, so this, for example, will be an example of a space where W1P of omega is just M1P of omega. Okay, so thanks for watching, and see you in more videos regarding Sobolev-Hajlasz classes.